let's start. Last time, I introduced the Wick theorem, which says that this complicated time-order product of many operators inside this unperturbed ensemble average is equal to sum of all possible fully contractions, which means that you could fully contract all possible pairs of two operators, A, B, C, up to F, and you sum over all such fully contractions. And assuming that this tau A is larger than tau B all the way to tau F. And so let's provide the proof today. Okay? So to prove this Wick theorem, we need to introduce this kind of second quantized fields of psi and psi dagger. So the psi dagger x tau in the imaginary time representation is given by this time of decomposition, where J refers to the sum over all possible J. So J refers to the eigenstates, the complete set of eigenstates. So you could decompose this psi dagger of psi in terms of complete set of eigenbases, and in that basis, this alpha J refers to the operator, and chi J refers to the sort of a Fourier coefficient. And you could also do the same thing for this psi destruction operator. So let's just write down this chi of J, which is the Fourier coefficient. So in terms of the Fourier decomposition, this chi J is given by this spatial part of the Fourier coefficient multiplied by this time or imaginary time evolution, right? So because this is, remember, the operator in the interaction picture. Okay, so if you fully decompose this psi of psi dagger in terms of the special part of this operator in this expansion, multiplied by this time or imaginary time component, and also multiply by this operator. So alpha J refers to just a creation destruction operator. So here I don't care about this alpha J or alpha dagger J, so I simply just use the alpha J to represent this kind of upside dagger, but you will see that it doesn't matter later. And you could define this psi in the same way. So, and you plug in such a kind of operator decomposition back to this time order product. So now the product among the A, B, C up to F, taking this unperturbed ensemble average, is given by all this summation over all this chi and phi and this alpha, right? Of course, there's an imaginary time factor here, which is actually omitted, and I use this dot, this dot to represent all the remaining factors which don't play a role here. And also this phi 0 j of x, this is also just kind of a coefficient, and all these prefactors are hidden here. This chi A, chi B, and up to chi F. And so those chi's are simply just prefactors or coefficients. So the most important part of this identity is the operator inside a trace. And so we are going to use this commutation or anti-commutation relations to actually contract all this alpha A up to alpha F inside the trace. All right, so alpha A up to alpha F are creation or destruction operator. And they satisfy this commutation or anti-commutation relations. Right? So if alphas are bosons, they satisfy the commutation relation. If they are fermions, they satisfy the anti-commutation relations. So the alphas are operators, and the chi's are all coefficients, which are not so important here. Okay, so we are going to take advantage of this commutation or anti-commutation relations between the alphas to simplify this trace. Okay, so this is the way to go. Okay, so the way to simplify this is to commute this alpha A successively to the right. So alpha A is here. So we would like to move alpha A all the way to the right. Okay? And by doing so, we could take advantage of such a commutator or anti-commutator between the alphas. And then simplify this on the trace, because once we, as you know in just a moment later, that if you apply this commutator, and these two operators will be gone. And let's see this. Okay, so this is going to be alpha A commute or anti-commute with alpha B, and then all the way to alpha F plus minus alpha B, alpha A, alpha C, minus plus, and plus and all the way to the very end. Okay, so we try to move this alpha A all the way from the very left to the very right. So you need to pass through all these intermediate alphas, and when you pass any one of the alphas, you need to exchange those operators. When you exchange the operators, you need to use this commutation or anti-commutation relations, but you need to use it m multiple times, right? Because you need to interchange of all the alphas between A and B and what? A and C and A and D all the way to A and F. And that's exactly what we write here. The first exchange is between A and B, and plus minus, the second exchange is between A and C, and so on and so forth. So the last exchange is between A and F. And finally, the alpha F appears on the right. And by doing so, we simplify this trace because remember this alpha A, alpha B commutator or anti-commutator is nothing but a number, right? And this trace right here has only m minus 2 operators because these two operators are gone. Because this is just a number called commuting number or C number. So this is just a number, so you could easily pull them out of this trace, and then inside the trace we have two operators less, right? Two operators are gone already because they form a commutator, anti-commutator, and they are C number, so you simply just move them out. Okay, but this is not the end of the story because you have this alpha C here all the way to alpha F, and they are operators still inside the trace, so you need to perform such trick to move the alpha C all the way to the very right. And then you follow the same path until you pair them up all together. So let me just go step by step. So since alpha A, alpha B, C numbers can be taken outside of the trace. Okay, but there is an additional point that I need to make, which I will probably write here. So when we make such a move, we have to remember that there's a relation between this kind of unitary transformation that takes you from alpha A to alpha A at times this energy prefactor, where this lambda A is actually plus 1 if alpha A is a dagger, which is a creation operator. If lambda A is minus 1, alpha A is destruction operator, or vice versa. So for A dagger, alpha A is 1, and for A operator, alpha A equals to A, lambda A is actually minus 1. So this is kind of a unitary transformation that when you really want to pull this factor out. Because when you pull them out, you need to, so you could simply just directly pull them out, but you could use this relation to actually further simplify your expression. And so let's take a short break. When we come back, we will take advantage of such a unitary transformation and then just to rewrite this trace by using this identity. So let me just make one more remark. So this relation will be used when we try to rewrite this last term right there. Okay, so we will come to this just a moment. Okay, so let's continue. So the last identity that I introduced a moment ago is this. This is a unitary transformation which transforms this alpha A from tau equals 0 to tau equals beta, and after this transformation, on the right-hand side of the equations is given by lambda A times this sort of imaginary time evolution factor. Okay, so this is analogous to the, say, time evolution of your Heisenberg operator. So remember that in the real-time representation. So imaginary time representation, this is sort of an imaginary time evolution of your operator in the interaction picture, right? So if you have this relation, and immediately you could translate this relation to the second line here, where you could replace this e to the beta k0 and this factor, and you could use this density matrix rho g0 that we introduced earlier, which is nothing but this factor divided by this partition function. And then you could rewrite this equation up here in the second line here, where this alpha A times rho g0 is the same as rho g0 times alpha A and times this extra imaginary time prefactor. Okay, so I think rho g0 is nothing but e minus beta k0 divided by z. Okay, so if somehow you multiply this rho g0 on both sides, and you get the second line. Okay, so, and this identity is very helpful for us to reformulate the very last term. What is the very last term? Which is plus minus trace rho g0 alpha b alpha c alpha f alpha a. Right? So this is the last term when we successfully commute this alpha a all the way from the left to the right, and then we can rewrite this, the last term, by using this identity right here. And then this is going to be alpha a rho g0 alpha b alpha c alpha f, which is plus minus e to the lambda a beta times trace rho g0 alpha a alpha b alpha c alpha f. Okay, so the very last term right here looks very similar to the very first term that we start with. Remember, the first term that we start with is the term, so the first term, rho g0 alpha a alpha b all the way to alpha f. Or in the very beginning, okay, so in the very beginning, initial. Okay, and remember this initial trace is given by all these commutators and so on and so forth, right? Okay, but the very last term, it looks very similar to the very first term in the beginning on the left-hand side of the equation. So except the orders between alpha a and alpha f are different, because initially this alpha a up to alpha f appeared on the right of this rho g0, but the last term when we use this commutation relations, and this alpha a could actually move all the way to the very left, right, of this rho g0, but this is not a standard order that we usually define on the trace. And so we need to interchange this alpha a and rho g0, and when we do the interchange between alpha a and rho g0, we should use this identity in the yellow box. Okay, so as a result, when we switch the order between alpha a and rho g0, and we get the actual factor of exponential lambda a beta times this energy factor. All right? And then so after this interchange, the last term has the same convention that we did in the very beginning, right? So then you could have a relation between the very first term and the very last term, because initial trace is given by this rho g0 alpha a to alpha f. Then you use this commutation relations. You can show that this is given by trace of those commutators plus minus another trace and all the way to this last one. So I use different color. The last one is rho g0 alpha b alpha f alpha a. Then you could actually rewrite this last term in terms of the very first term on the left hand side of the equation, which is given by this thing, right? So you could simply just use this relation, rewrite this term in terms of this term. But what is this term? Well, if you forget about this exponential factor, this trace, this term, this partial term is exactly the same as the initial term appearing on the left-hand side of the equation, right? So then you could simply just relate this, the first and the last term. So let me just summarize what you will get after using such relations, right? So the trace of rho g0 alpha a alpha b up to alpha f is going to be alpha a alpha b commutator divided by 1 minus plus e to the lambda a beta epsilon a 0 minus mu and times the trace 0 alpha c alpha d alpha f and plus minus alpha a alpha c plus 1 minus plus lambda a beta trace of 0 b alpha d up to alpha f. And all right, so once you take advantage of such a relation right here and to rewrite this last term, and you know that this last term has the similar structure as the very first term in the beginning, except we have this energy denominator, this energy factor right here. So this is going to be, let me just rewrite here, plus minus e to the lambda a beta epsilon 0 minus mu times same trace, right? Okay, so you see that this, on the left hand side of the equation, on the very top, this is the same as this one, right? Okay, so now you could actually move this all the way to the other side of the equation, right? To combine these two. Okay, and that's the and then you divide this, the whole thing, by this 1 plus minus e to the lambda beta epsilon 0 minus mu, and that's the reason why you have this denominator right here. Okay, so this 1 minus plus times this exponential factor of the energy and temperature is precisely coming from this factor right here. Okay, so this is 1 times the trace, but this is plus minus e to the something times the same trace, so you could actually combine these two. So you get 1, say, minus plus times e to the some exponent, and then you divide that prefactor, and this is precisely the denominator right here. And then you could actually divide the same factor to all these different terms when you actually move this alpha a all the way to the very right. Okay, so you get many, many terms. And then now, but the last term is the same as the first thing, except this prefactor. So you can combine these two. And then you divide this common factor and then this is the initial term, right? This is the initial trace. So now we are successful because we simplify the initial trace by rewriting the initial trace in terms of a simplified trace, because now all this trace on the right hand side of the equation contains two operators less, because the remaining two operators are precisely inside the commutator or anti-commutator, which becomes simply just a C number, and you get some C number as a prefactor divided by this e plus minus this exponential term and times this simplified trace. So you got to say n minus 2 operators remains in the trace on the right hand side. But this is not the end of the story, because this is not yet done. There are still n minus 2 operators inside the trace, so you need to perform the same trick that we did for this alpha A and alpha B. So you need to move alpha C all the way to the right of alpha F. And then you will get the same thing, similar terms like this, and you could further simplify the trace. After the second motion or exchange of these alphas, you get two operators less, which means that this after the first exchange, you go from n operators to n minus 2, then you go to the second steps. So you go from n minus 2 operators to n minus 4, and then go on and all the way to, I don't know how many steps you need, from 2 operators, no operators at the very end of this. So now let's just define this contraction between alpha and alpha B by including this denominator right there. So I call this alpha A dot alpha B dot, which means that when we fully contract this alpha and alpha B, and then we can move around all these terms inside the trace, and finally we get this prefactor. So this alpha A dot alpha B dot is the same as this commutator or anti-commutator between alpha and alpha B divided by this denominator. And this is called the contraction of alpha A and alpha B. So we will take advantage of such a notation, and then we will continue to contract all the other pairs of operators. So let's take a short break. So you will see later that this kind of derivation can actually help you derive this Fermi-Dirac and Bose-Einstein distribution function for fermions and bosons operators. So one more remark. As I mentioned, this alpha A and alpha B could be A or A dagger, C or C dagger, and you could have A commutator or anti-commutator, which vanishes, or A dagger, commutator or anti-commutator also vanish, right? So the only non-vanishing terms of this commutator or anti-commutator are C dagger or A dagger or A dagger A or C dagger C, that kind of pairs that will survive. So in other words, most of these contractions are zero, because if you contract between these two destruction operators, it is zero. If you contract two creation operators, it is also zero. So only if you contract one destruction and one creation operator do you have a finite result, and that is coming from this commutation, anti-commutation relations between the fermion and boson operators. So let's just use this notation, alpha A dot, alpha B dot, to rewrite this complicated trace. As I mentioned, this is given by alpha all possible contractions. So now we simply just contract alpha A with the other one operators in the remaining product inside the trace, and this is given by this, and all the way to the very end, alpha A dot, alpha F dot, trace 0, alpha B, alpha C, alpha E. And here comes my remark. So in practice, most terms vanish. So the only non-zero term are this. Right? Okay, as mentioned, the only non-zero terms come from the terms that you contract one creation and one destruction operator, because this is the term that survives. If you look at this commutation, anti-commutation relations between fermion and boson operators, and a minus term refers to the boson and plus term refers to the fermion. So you see this is precisely this Fermi-Dirac and Bose-Einstein distribution function, which is minus plus 1, 1 minus plus e to the beta epsilon mu, which is 1 over e to the beta, say 0 minus mu minus plus 1, which is n0, Bose-Einstein and Fermi-Dirac. So this is the way to derive the Fermi-Dirac and Bose-Einstein distribution function. Okay, sounds magic. So we don't know about the statistical mechanics. The only thing that we know is the commutation, the anti-commutation relations, and the Green's functions. And remember, this is precisely the number operator. In the fermion electron systems, and this is nothing but electron occupation satisfied this Fermi-Dirac distribution. And this is also this boson number, occupation number, which is the Bose factor.
Epsilon J0 equal to mu, so it's divergent.
You mean whether this epsilon J0 could be equal to mu? In the fermion system, of course it can, right? But in the boson system, it depends on what kind of bosons that you are dealing with, okay? For this, the BEC bosons, where these bosons could populate the ground state, mu could be 0. But for these quasi-particles, for example, the phonons and so on, you don't get condensation of phonons, right? You don't get condensation of magnons because those are quasi-particles. For quasi-particles, mu cannot be 0. But in general, this is true, right? So I don't care whether mu could be or cannot be 0. So mu is always there. So this is true for all quasi-particles or non-quasi-particles or whatever boson fermions that you are talking about. This is true in general, okay? And in similar way, so you could show that the reverse contraction between A and A dagger, which I call this AJ dot times AJ dot dagger, this is given by 1 plus minus and J0. It's obvious. So now you are able to really do this exercise that you can show that the Green's function at finite temperature or imaginary time Green's functions, if you take the imaginary part, you could get this Fermi-Dirac or Bose-Einstein factors by using this kind of a derivation. So let's continue. So I could just define officially this contraction between alpha and alpha b with respect to the unperturbed Hamiltonian like this. So suppose tau A is larger than tau B, and I could call this contraction between alpha and alpha b this time-ordered ensemble average with respect to this H0, and this is nothing but unperturbed single particle Green's function, right? So this is unperturbed single particle Green's function. So in other words, it's alpha A dot, alpha B dot is nothing but unperturbed single particle Green's function. But I haven't finished everything yet because now I simply just remove two operators from this complicated trace, but you could finish the job by contracting all the other alphas in the remaining part of the trace. So this is your homework. Finish the job. And you could play the same game as we did before and contract all the remaining alphas. And by the end of the day, of course, the number of alphas should be even. Otherwise, you don't get a fully paired. Because if you have an odd number of operators inside the trace, you get 0 because you don't get any. You don't get fully paired operators. But in the case of even number of operators inside this trace, you could form pairs for all the alphas. And just play this game repeatedly, and you'll find that by the end of the day, this is nothing but the product of fully contraction. It's a sum of all possible fully contracted pairs. And this is the essence of Wick theorem, which significantly simplified the computation that we need to do in order to perform this Green's function calculation. So, and I think this is very clear that I don't need to go to the very end. I think you could finish the job by yourself and convince yourself that indeed you could further pair up all those alphas by moving around all those alphas and use those identities, and you'll find the same results, except now after one more pairing, two more operators are missing, not missing, just are pulled out of this trace, and then another 2 more, another 2 more, until there is no operators inside the trace, and then you are done. So you can imagine that when you are done, and this is nothing but many, many terms to be summed over, but each term contains this one possible fully contractions of weak pairs. Of course, as I mentioned, those alphas could be either creation or destruction operators, and only a finite number, a small number of terms survive. And oftentimes you'll encounter such weak pairs between C and C, or C dagger and C dagger, which are both 0. Although in general you need to sum over all possible fully contracted weak pairs, but in practice there are only finite number of terms that survive that you need to sum over, only a handful of terms, maybe 1 or 2 terms or 3 or 4 terms out of 100 terms. So this greatly simplifies this calculation of this trace, and then we will come back to this later when we talk about this Feynman diagram, Feynman rules. So let's take a short break. Any questions so far? Okay, so it takes some algebra to really see this result, but I believe you are able to do so. Okay, and you can also read these corresponding chapters in Flansburgh or other references, which has all these equations I just wrote down. So next thing is to simplify further all these weak pairs that we did by using this Wick theorem. So let me just rewrite this one more time. So at the end of the day, what you will find is that you have to sum over many terms like this. Each term is simply just a complete product of all the weak pairs. For example, if you find one term looks like this is alpha A dot, alpha B dot times alpha C dot, alpha D dot, until the very end pair. But you know very well that if any of this pair is actually CC or C dagger, and they are gone. Right? Okay, so you have many, many terms like this, but most of the terms are 0. Because imagine that these alphas are simply just creation and destruction operators like C. So C, 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 C dagger, C dagger, C dagger. So this is, say, 1, 2, 3, 4, 5, 6, for example. Right? So suppose we have 6 operators. 3 of them are destructions, and another 3 are creation operators inside the trace, and you need to form all possible weak pairs, and one term will look like what? C1, C2 contraction, C3, C4 dagger contraction, and C dagger 5, C dagger 6 contraction. So you know immediately that this term vanishes because this is 0, because 2 destructions. When you contract them, you don't get anything, and so on and so forth. So the only possible term that survive are the terms where you contract one destruction with one creation, like this, like this. Okay, if you pair C1 with C4 dagger, C2 with C5 dagger, and C3 with C6 dagger, then this is surviving. But this is not the only term that you can have, right? So how many terms can you have? Can anyone tell me? That's the high school problem, right? And another term that survives are this say 1 pair with 6, 2 pair with 5, and 3 with 4. Yes? And anything else? 1 with 5, and 2 with 4, 3 with 6, and so on and so forth. Okay, so we will, arrive such kind of pairing in just a moment. Okay, so and you see that there are not so many terms survive. So let me just make a remark. When we calculate, in calculating this thermal average or ensemble average, statistical average, so each pair can be averaged separately. Okay, so and this is, the great advantage that the Wick contraction theory provides with us, because remember this alpha A dot, alpha B dot is nothing but unperturbed single particle Green's function, right? So the whole thing is nothing but the summing over all possible Wick contraction pair, but inside each term, it is nothing but the function of single particle Green's function, right? So this is precisely what I mentioned previously, that even though this is a highly interacting system with H1 and H0, but at the end of the day, this is simply a function of single particle unperturbed Green's function. Of course, we need to multiply this coupling constant in front of each term, right? But other than that, all this complicated trace is reduced to simply just summing over all possible functions of a single particle unperturbed Green's function. Okay? So therefore, the fundamental object is a single particle unperturbed Green's function, and then you could build up all this interacting Green's function in terms of the function of a single particle unperturbed Green's function. So we will see this in the concrete example. So let me just finish this statement. The average of a time-ordered product, sum of all possible average over all pair of operators. Okay, and of course it's unperturbed. So let's just take a concrete example. So here is the simplest possible non-trivial example is this full operator Green's function. Suppose I have this trace, this thermal average of time-ordered product of operators, psi, dagger, it's 4 different space and time coordinates, and you try to apply this Wick contractions. Of course, you need to sort of Fourier transform these operators and take advantage of this unitary transformation and interaction operators and separate this spatial part of this operator from this creation destruction operators that depend only on time. So you could separate out the spatial and Fourier coefficients from these operators, which are function of time. So let's perform this Fourier transformation. Let me just give this detail. We have defined these Fourier transformations earlier. So you simply just Fourier transform these 4 operators independently, and therefore you need to sum over how many momentums? 4 momentums labeled by P1 up to P4, and you have those exponential Fourier coefficient, and also you have this imaginary time energy factor, and then you need to multiply it by the thermal average of these operators. Right? Okay. So these complicated exponential factors are not so important, but the most important part is this thermal average of this 4A and A dagger product at different times and different momentum. So now we could use our very useful Wick theorem to simplify this. So let me just use different colors to represent different way of pairing. So you could pair P1 with P4 and 2 with 3, and you could also pair up 1 and 3 and 2 and 4. What else? Any other possibilities? No, because all the other possibilities are 0. So this is the simplest possible Wick pair you can form among 4 operators, 2 destruction and 2 creations, and then you simply just apply these Wick rules to simplify this, given by sum over P1, P4. Remember, each of this Wick pair, when you contract them, will be evaluated independently, separately. So let me just collect all these factors for each of these Wick pairs. And another pair, 1 and 3, 2 and 3. And the other term. So as I mentioned, each of this weak pair will be evaluated separately. So you could define, as I mentioned, this weak pair in terms of the alphas. But you can also define this in this more standard or more conventional form, which is the product of the psi 1 and psi dagger 4 with the time order. So let me just define this. So you can actually perform the inverse Fourier transformation, and you can combine this Fourier coefficients with this A and A dagger weak pairs, and then you could redefine this psi 1 and psi dagger 4. So this is given by time orders psi 1, x1 tau 1, psi dagger 4, x4 tau 4 times 2 and 3 and plus the other term. So this sounds really easy and simple. And since you know this, next time when you decompose this 4 operator inside the trace, you don't bother performing the Fourier transformations anymore because you know very well it will be given by time ordered psi 1 psi dagger 4 times time ordered psi 2 psi dagger 3, right? And the other orders. So next time we don't bother writing down the Fourier expansion of these operators. We simply just go directly from here all the way to here. So you can simply look at this product and you can see that this is one possible contractions and there is another possible contraction right here. But what are they? You know what they are. We already defined this previously. This is nothing but the single particle unperturbed Green's function with respect to H0, and you know very well. The only thing that you need to do is to make a product of this Green's function here between 1 and 4, and then another Green's function between 2 and 3. That's all. The only thing that you need to do, not the only thing, but this is complicated enough, but the remaining task is to really calculate this product of many single particle Green's functions. For example, this is a simple product between 2 non-interacting Green's functions for a single particle. And you know them. You just make a product and that's all. But this is not the end of the story. You need to add the other term. However, this is simply just the simplest possible you can imagine to apply the weak contraction. But for higher order terms in this Taylor-like expansion of this S matrix, you know that, right? So this operator inside the trace and inside the time ordered operation is actually to be exploded because the number of operators is actually increasing more and more if you go to one more order higher. So then this is the lowest order. So what is the second order? Maybe 6 operators. And for 6 operators, you have many more terms that you can perform weak contraction. What about 8 operators, 10 operators, 12, 14, 20, 30, 50, 100. When the number of operators increases, this kind of weak pairs that you can form become much more complicated than you can handle. So as a result, a smart physicist named Feynman invented a way to systematically just list all possible weak contraction pairs and use diagrams to simplify all these complicated terms. So you don't bother writing down this mathematical equation and formulations. The only thing that you need to do is to define a convention and define graphs and diagrams. And each diagram represents each of these weak, fully contracted pairs, and then use so-called Feynman diagrams to simplify all this perturbed expansion in the presence of interactions. And this is the story before we introduce the Feynman diagram. So it's a very simple exercise that you could do at home. Suppose that you try to simplify it and make weak pairs for 8 operators inside the trace. What would you find? So you could derive those weak pairs today, and you could rederive those summations tomorrow, and you'll find that your answers will not be the same. So each day, you'll find different answer. That's the problem, because it's very difficult to make a bookkeeping notations if you don't introduce a Feynman diagram, Feynman rules, something like that. So you will be trapped inside this minus sign problems and the factor of 2 and things like that. So I think the most troublesome issue is the minus sign, okay? Because when you form the weak pair, you need to move around all these operators, and you need to will keep the orders in your Taylor expansions. For example, in third order, you should carry a minus sign relative to the second order, and so on and so forth. So there are many sources of minus sign that you need to worry about. And that's why you can have all different answers if you do the same exercise at different time. And we need a systematic way to avoid such minus sign errors and mistakes. And this comes the Feynman diagram. So the Feynman diagrams are diagrammatic or graphic representation of all the terms in the perturbed expansions with a simple rule for the actual calculation. So that was introduced by Richard Feynman. So then we will introduce those rules and use those rules to draw the diagrams. Of course, when we know the rules, we could actually forget about all this perturbed expansion and this minus sign, this kind of issues, and then just stick to the Feynman rules. So let's just use an example to illustrate this Feynman diagrams. Suppose we are looking at this spin-independent identical particles and spin-independent interactions. H1 is given by, those particles carry spin, but their interactions are spinless. So spin-independent interaction. So suppose this is two particle interactions. It could be Coulomb interaction, for example, or other type of interactions. Suppose these interactions are between density of these particles. Okay, so it's density-density interactions. And the Coulomb interaction is one example of this density-density interaction. So I can rewrite this density-density interaction in terms of this density of particles in real space, and n of x refers to the density of particles, psi dagger alpha, psi beta, and so on and so forth. So, or psi dagger alpha, and psi dagger beta, psi beta. Okay, anyway. So you can form two density operators, n of x and n of x prime, and these two densities interact with one another through this u interaction, u, which is a function of the distance between these two operators. So n of x sum over alpha, and u is a potential term. So this term is very similar to Coulomb interaction, which we will come back later to actually calculate the effects of the Coulomb interactions on this electron gas or ordinary metals. But here it's just some toy model. So that's introduced a more general form of the interaction, which we call V, which carried not only the spatial degrees of freedom, but also time degrees of freedom. And its four coordinates is labeled by x and tau, where tau is nothing but the imaginary time. So remember, we are talking about imaginary time Green's functions, but we need to generalize this interaction, which depend only on the spatial degree of freedom, to the interaction depends both the spatial and temporal degree of freedom, but this time degree of freedom is actually the imaginary time here, so that we could more conveniently perform this perturbation. So the reason why we need to define this time coordinate to this interaction is that we could really tell when this interaction occurs. So before the interaction introduced, before they scatter, and then after they scatter, so they may differ by a finite amount of time. And we will need to distinguish the time that the particles interact. So then this integral in the perturbative expansion will actually contain this 2 times d plus 1 dimensional integral, because this h1 has actually 2 spatial integrals. So each spatial integration is actually what d-dimensional integral, right? So you have 2d dimensional integral, but then you add this temporal degrees of freedom, and so the tau here, so you need to integrate the tau twice, so you add this 2 more dimensional integral there. So it's 2d plus 2. So let's just try to estimate the lowest order in perturbation, just up to linear order in V, and we call this, maybe I write here, delta italic G alpha beta first order, 1 and 2, which is following the definition. So the spatial dimension is 3, so, and the dz integral is actually 4-dimensional integral. Now we have different coordinates, the z's and the x. Okay, so by this second order in perturbation, so we could write down this G alpha beta 1, 2 up to the lowest order, which is the first order in perturbation, which is linearly proportional to V. So let me just distinguish this operator in the original Green's function, which is labeled by x1, x2, and the other 4 all comes from H1. Because H1 has 4 operators. And I could generalize this U to add this time degrees of freedom, and therefore my H1 integral involve this 2 4-dimensional integration dz1 and dz2. And therefore we can combine all this spatial and temporal degrees of freedom, and I could easily tell whether this operator comes from the original operators or the operators in the H1. So all these operators that come from H1 carry this variable z, while these original operators carry only spatial coordinate, x, x1, and x2. But of course, we could generalize this x1 and x2 to the 4-dimensional coordinate, which means that this is x1 tau 1 and x2 tau 2. So now we have how many operators are there? 6. This is my first example. So how many terms are there that are finite? There are 8 terms that are non-zero of 3 pairs of single particle operators. So in other words, this has 8 terms. But what are those 8 terms? We could take a break, and when we come back, I will illustrate and write down all these 8 terms. And later, when we simplify these 8 terms, we could use diagrams to actually represent all these 8 terms. So each diagram could actually represent 1 term. So let me just write down all these 8 terms. Remember, when we write down these time-ordered operators, what we mean that when tau 1 is greater than tau 2, we follow this convention, but the other way around, we should remember to add this plus minus sign. And also z1 is greater than z2. Yeah, you could check this plus minus sign if you agree with the sign. So let me just explain this 8 terms in terms of 2 4 terms. And the other 4 terms could be derived by exchanging this z1 and z2. So the first 4 terms are these 4. 1, 2, 3, 4. So let me just go through all these terms. So the first term is this time ordered given psi alpha and psi dagger beta, x1, x2. And then we don't know whether this x1 is actually larger than x2 or not. But we only know that this tau 1 is actually larger than tau 2 and z1 is larger than z2. And so then we need to put this time ordered. But the second term is the already time ordered psi j z1, psi dagger j z2 pair. So this pair, the z1 appears on the left, the destruction operator, and z2 on the right, which follows the standard time convention. And as a result, we don't need to put the time order because they are ordered already. And so is the third pair. So I suppose this is k z2, k j z1, and so these variables are the same. So we don't need to put the time order there. So is the other pair. So let me just look at the second term. So the first term is actually clear, and the second term is that the second term is j, right? So k z2 pair with j z1. So then z2 is actually smaller than z1. So then we need to flip the sign. And what about this j dagger z1 and k z2? So z1 is greater than z2, so that's fine. And you can actually try yourself for the other 2 terms and all the other 4 terms by exchanging z1 and z2. So, and I don't want to assign this to you as a homework exercise, but you need to verify all these prefactors plus minus 1 and also the orders between the psi and psi dagger, and whether you put this time ordered operator or not. So if you know already the order between these 2 variables, then you don't need the time order operator anymore. But if you don't know, then you need to know. You need to put this time ordered operator. Okay, so, but this is really complicated. Let me just call this term A and B and C and D. So Feynman invented a way to use diagrams for all these different terms. So let me use the Feynman rules for Feynman diagrams. First, the point in the plane represents a set of coordinates. So x is again the 4 space-time vector. The 3-dimensional spatial vector is represented by the r, and tau is the imaginary time, and j refers to spin. You put this point, a space-time plus spin, on all these operators that depend on. So that's what I did. So I associate all these operators with a point in this xj plane, where the x refers to these 4 vectors, and j is a spin index. And then you connect all those points in the argument of G0 by a solid line directed from creation operator on the right to the destruction operator on the left. And number 3, you connect points in the argument of this V, the potential term, by a wavy line. So let me just repeat what I just wrote down here. So first you attach space, time, and spin index to all the operators. And then you connect the points in the argument of the Green's function, upside dagger, and with a solid line, where the solid line goes from the creation operator, upside dagger, on the right to the destruction operator on the left. And the next thing is you connect the points in the interaction term, V of Z1 minus Z2. You connect this Z1 and Z2 by a wavy line. So let me just write down all these diagrams that you find. So this is the first term, and B, sorry, there is an overall minus sign here. So we should multiply this by minus sign, and minus sign, and minus sign. Sorry. And the sign for this diagram A is -1, and diagram B is this, minus plus, and diagram C, this one, carry minus plus, diagram D, this. Okay, so let's very briefly just make such a connection between the diagrams and the terms. So the first term is this 2 bubbles connected by a wavy line and disconnected to the solid line here. So let's look at the solid line first. The solid line refers to the first weak pairs between x1 and x2. So you draw the solid line from x2, which is the creation operator on the right, and then go to the left where this coordinate is actually x1. So from x2 to x1, you draw a solid line with the arrow. So that's indicate the first weak pair. The other 4 operators formed by these 2 weak pairs are those 2 bubbles connected by a wavy line. First of all, there's a V, Z1 minus Z2, which connect these 2 weak pairs, and then this is the wavy line in between. But what is the first, the second weak pairs in the middle? So this is a loop, because you start from the side dagger on the right, which is Z1, and you go back to Z1. So Z1 start from here, and then you end at the same point, Z1, which form the loop. And same for the other loop that you come from Z2, and then you actually go back to Z2. So let me stop here, and this will be your homework problem. So you actually try to link these operators to the diagrams to the operators. Okay? And you may use words to express the link between the diagrams and these operators for the remaining 3 diagrams. So let's end our today's lectures now. So I see you next Monday.